This is lecture 23. So in this lecture we are going to discuss about the AC transients. In previous lectures we have seen sinusoidal steady state analysis. Only we are finding the steady state response. Now we will find the transient response and what is the condition for transient free response, right? Transient response plus steady state response. Both we will find, and what is the transient free condition, right? Now so we'll tell two important point, that is intensity of DC transient is more than intensity of AC transient, right? Now what is this meaning is, suppose in an AC circuit, that is if we apply some AC signal, though depending on the selection of the components or parameters, right, so inside the circuit, or depending on the operating frequency or switching operation, that is when we are the switch is closed or open, it is possible to design transient free condition or transient free circuits, but in the DC circuit it is not possible to obtain transient free response. Reason is, when we apply DC sources or DC signal to this inductor and capacitor, they are always oppose these sudden changes. But this when you apply AC signal, so it is a slowly increasing or decreasing function, so they will act so depending on the what is the frequency we are applying, right? So that's why we'll get a transient free condition in AC circuit. Now we'll start with RL network and the RC network, right? Suppose there is a RL network. So in this RL network, so switch is closed at t equal to 0, and V of t is a AC signal, which is I am taking as Vm sine omega t plus pi, right? Now so whatever we did for DC transient we will do. For t less than 0, what is the condition? Switch is open, that is only source free network, so that is RL, and this, what is the condition? The inductor will be short circuit because it is charged, but there is no switch is closed. What is IL of 0 minus is nothing but 0. That means initial current is 0 in the inductor. Now for t greater than 0, or so this is 0 minus, at t equal to 0 plus also IL of 0 plus is nothing but 0 itself, because it doesn't allow sudden changes. When t greater than 0, what is the circuit? Is nothing but whatever we have done, sinusoidal steady state analysis is same, that is RL, this is V of t, right? This is I of t, right? Now if I apply KVL, so minus V of t plus R into I of t plus L di by dt is equal to 0, right? Now what is this equation? L di by dt plus R I is equal to V of t. Now it's nothing but again it is a first order differential equation. This V of t is some function in t. So again we'll get two solutions, that is complementary function and particular integral, right? So the complementary function is nothing but the transient response, and this is nothing but steady state response, right? So we'll find both. Now to find the steady state response, so I will take L di by dt plus R into I is equal to 0. So this is for transient response. Now again it is a simple variable separable method. So di by dt is equal to minus R by L I. So 1 by I di is equal to minus R by L dt. If I integrate both sides, I will get a constant k. So 1 by x dx is nothing but ln x or ln I. This is minus R by L is constant. Integration of constant is nothing but variable, will get t. Right? So I need I. So I of t or I transient of t is equal to e power minus R by L into t into e power k. So e power k I am assuming as a, some constant k, right? Or we assume k any constant. So this is the transient response. This is also be found in the previous lectures. Next we will find the steady state response. Steady state response. So what is that one is? So this is L di by dt plus R I is equal to V of t, right? So we will have two approaches, Laplace transform approach or the phasor domain approach. Now we will do the phasor domain approach. that is like this. See, di by dt is there, so L into, so what it will become, S into I plus R into I plus V. Now what is this? If I take I common, it will become R plus SL is equal to V. So what is I? V by R plus SL. Now in phasor domain, S will become J omega L and V becomes Vm angle pi minus 90 degree, because V of t in the time domain is Vm sin omega t plus pi. So I already explained how it is. So this can be written in phasor domain, that is Vm angle, whatever the phase is there, pi minus 90 degree, because generally we take reference as cos signal. So to get cos, that is cos of 90 minus theta, I mean theta minus 90. So in place of theta we are having pi, so pi minus 90. So that is why we get. Now if I proceed again further, so what do we get? I is equal to 1 by R plus J omega L into Vm angle pi minus 90 degree. Now if I find this phasor domain magnitude, that is R square plus imaginary square, real square plus imaginary square into angle tan inverse omega L by R, because imaginary part is omega L and our real part is R, into this is pi minus 90 degree. If this is angle is going upside, so Vm by square root of R square plus omega L whole square angle pi minus 90 degree plus tan inverse omega L by R. This is the steady state response. Now this is in phasor domain. If I convert into time domain, so I steady state of t is equal to magnitude, that is Vm by square root of R square plus omega L whole square. So for this one, for this angle, we need to find the sine. So sine omega t, see this is theta minus 90. So only we will write theta, that is plus pi plus, so that is not plus. If this is plus is going up, so it will become minus tan inverse omega L by R. So minus tan inverse omega L by R. So this is the steady state response. Now if I write the total response, that is transient response plus steady state response. So this will become from A into e power minus R by L into t plus this value Vm by square root of R square plus omega L whole square sine of omega t plus pi minus tan inverse omega L by R. So this is the total response. Now to find the A, that is a constant, so we will use the initial value. So what is the initial value we got? I of 0 plus I of 0 minus is equal to I of 0 plus is nothing but 0, right? If I substitute in the previous expression, so 0 is equal to A into e power minus R by L into t, right? So t equal to 0 means it will become 1 plus Vm by square root of R square plus omega L whole square sine of omega t. So omega t means 0 plus pi minus tan inverse omega L by R, right? Now 0 is equal to A into e power minus 1, I mean e power minus 0 is nothing but 1 plus this is Vm by square root of R square plus omega L whole square sine of pi minus tan inverse omega L by R. So what is A here? So A, you will get minus of this one. So A is equal to minus of Vm by square root of R square plus omega L whole square sine of pi minus tan inverse omega L by R, right? Now if I substitute in this one, that is A I of t is equal to A, that is minus Vm by square root of R square plus omega L whole square sine pi minus tan inverse omega L by R plus actually into e power minus R by L into t, because it's a transient response, plus Vm by square root of R square plus omega L whole square sine omega t plus pi minus tan inverse omega L by R. So this is the expression. Now if you see this expression, suppose if this value is 0, suppose let at t equal to 0 and so at t equal to 0 the switch is closing, and this pi minus tan inverse omega L by R, suppose it is equal to 0. So t equal to 0 means e power 0 is 1, and this is sine of 0. Sine of 0 is nothing but 0. That means what we will get, I of t is now Vm by square root of R square plus omega L whole square into sine after t greater than 0, only this value will be there. That is steady state response. That is sine omega t. So if omega t is, so t equal to 0 means it will be 0. So we will get the steady state response as tan inverse omega L by R. Right? That means if you see this one, that is pi is equal to what? Tan inverse omega L by R. That means what is the transient free condition? That is the transient frequency, the transient free condition is what? When pi is equal to tan inverse omega L by R, then we will get I of t is equal to only steady state response. Right? So this is the steady state response. Only steady state response we will get when pi is equal to tan inverse omega L by R. Right? So this is about the AC transient for RL network. Now, in the previous case, we have assumed V of t is equal to Vm sine omega t plus pi. Then what is the transient free condition? So transient free condition is got pi is equal to tan inverse omega L by R. Right? Now if we apply V of t is equal to Vm cos omega t plus pi, now what we will get? So again, if it is in phasor domain, so Vm angle phi only we will get. Right? So Vm angle pi, if you follow the same procedure, so what I will get is I of t is equal to minus Vm by square root of R square plus omega L whole square. Here we will get cos pi minus tan inverse omega L by R, right, into e power minus R by L into t plus Vm by square root of R square plus omega L whole square into cos of omega t plus pi minus tan inverse omega L by R. So this is the total response we will get. Now again, see, we can make this pi minus tan inverse omega L by R into pi by 2. Suppose let pi minus tan inverse omega L by R is equal to 90 degree. Then only cos pi by 2 will become 0. So to make the transient free condition, so cos pi by 2 should be 0. So pi minus tan inverse omega L by R equal to pi by 2. That means I of t will become only steady state response. So what is the transient free condition when we apply cos signal? So transient free condition is pi is equal to tan inverse omega L by R plus pi by 2. Only when we apply cos signal, plus pi by 2 will be added. That's it. Right? So same for RC network, etc. So these are the two conditions for sine signal and cos signal. Now the switch is closed at t equal to 0 in the previous condition. Suppose now the question is like this. This is at t equal to t naught, and it is switch is closed. This is R L and this is R. Here we apply the V of t. Again, V of t is equal to Vm sine omega t plus pi. Now what will happen? Now the switch is closed now at t equal to t naught. Now the total response will change now, right? So you can easily write I of t is equal to A into e power minus R by L into t. So into t, in place of t we will get t minus t naught, right? If t naught equal to 0, so we'll get e power minus r by l into t. Now the switch is closed at after some time, that is t naught, so it will be delayed version. Plus here we will get same, that is Vm r square plus omega l whole square into sine of omega t plus pi minus tan inverse omega l by r. Now may I ask, in here we taken t minus t naught, but here we did not take t minus t naught. This response is after switch is closed. After switch is closed, it is v of t, l and r, so we can apply the same KVL, then we can find the same steady state response like this. Only the transient free condition will change, right? Again, if I apply this at t equal to t naught, I of t equal to 0, right? So that means I will get a here at t equal to t naught. What is I of 0? Is nothing but 0. Sorry, I of t naught is nothing but 0, that is at the closing of the switch. So again you will get a is equal to minus Vm by square root of r square plus omega l whole square sine of, so t equal to t naught, so this is omega t naught plus pi minus tan inverse omega l by r. Now if you see in the previous case at t equal to 0 we got sine of, this is 0 plus pi minus tan inverse omega l by r. Now it is at t equal to t naught, so omega into t naught. So the total response now it will become like this. I of t is equal to minus Vm by square root of r square plus omega l whole square sine omega t naught minus plus pi minus tan inverse omega l by r plus the next remaining same, that is Vm by square root of r square plus omega l whole square sine omega t plus pi minus tan inverse omega l by r. So this is steady state response and this one is transient response. Now again to make transient free condition, so this is into e power minus r by l into t minus t naught. Now to make this whole term 0, so we have to make sine of 0, right? If omega t naught plus pi minus tan inverse omega l by r equal to 0, that means we'll get I of t is only steady state response. Now what is the transient free condition? So here omega t naught r, so only pi here, or omega t naught is equal to tan inverse omega l by r minus pi, right? Or simply omega t naught plus pi is equal to tan inverse omega l by r. Anyway you can write, right? Omega t naught plus pi, because in previous case t naught equal to 0 means pi is equal to tan inverse omega l by r. Now it is omega into t naught plus pi is equal to tan inverse omega l by r. If v of t is equal to Vm cos omega t plus pi, suppose, how it will change? Only plus pi by 2 will be added, so omega t naught plus pi will be same. Here we will get tan inverse omega l by r plus pi by 2. Right? This is the transient free condition when signal is Vm cos omega t plus pi. Right? I hope you got some idea about this transient, AC transient. Next we will go for the RC network. Right? Same procedure we need to follow. Just pause the video and do on your own first, then compare. So again at t equal to 0, this is R, this is capacitor C, this is V of t. So what we need to find? Suppose we need to find Vc of t, right? Or I of t also. So same procedure we need to follow, right? So first we will find Vc of 0 minus, which is equal to Vc of 0 plus is nothing but 0, because when the switch is open, nothing source is connected, so the initial voltage is 0, right? Now to find the transient response and the steady state response, first write the KVL across this one, right? or very simple. So this is VC of t, right? So apply the nodal analysis here, right? So if I apply nodal analysis, VC of t minus V of t by R plus I need current, so it is C into dVC by dt equal to 0. So this is, we can write, because we need to find the voltage VC of t here, right? If you want to find current, then we can find the same procedure as the previous series. Now if I take C dVC by dt minus V of t by R, that is VCT of plus VC of t by R is equal to V of t by R. Now what it will become? So if I take C outside, so dVC by dt plus 1 by RC VC of t is equal to V of t by RC. So this is the equation 1. Again it is having the V of t is a with respect to time it is varying. Then we have to again two conditions, complementary function and particular integral. Now to find complementary function or transient response, what will take? dVC by dt plus 1 by RC into VC of t equal to 0. Again variable separable method, so it will become 1 by VC dVC is equal to minus 1 by RC into dt. Again if I integrate, I will get a constant, so it will become ln VC is equal to minus 1 by RC into t plus k. So it will become VC of t, right, which is transient response. VCTR of t is equal to some constant a into e power minus t by RC. So this is the equation 2. This is a transient response, e power minus t by RC. Next, to find the particular integral, so we follow the same procedure, that is for phasor domain approach. Let V of t is equal to Vm sin omega t plus pi. What is in phasor domain? It will be represented by Vm angle pi minus 90 degree. So what is the equation? That is dVc of t by dt plus 1 by RC into VC of t is equal to V of t by RC. Now if I take the differentiation, that is S into VC of S plus 1 by RC into VC of S is equal to V by RC. Now phasor domain, so it will become VC of j omega. If I take common, so it will become S plus 1 by RC is equal to V by RC. Now if I take this here RC common, so VC of VC in phasor domain, so V by, so RC cancel, it will become 1 plus S into RC. So in phasor domain, if I write, what is V? Vm angle pi minus 90 degree by 1 plus RC, that is 1 plus j omega RC. So this is VC. Now how to find this one? So Vm angle pi minus 90 degree by square root of 1 plus omega RC square angle tan inverse, see imaginary part by real part, so omega RC. So if this is angle going up, so the VC in phasor will be like this. VC is equal to Vm angle pi minus 90 degree minus tan inverse omega RC by square root of 1 plus omega RC square. Now what is the VC of t? That is steady state response. So magnitude as it is Vm by square root of 1 plus omega RC square. So it will become sin omega t. So 90 degree will not come, right, because pi minus 90. So what is the pi? Pi minus tan inverse though, plus pi minus tan inverse omega RC. So this is the steady state response. Now what is the total response? VC of t is equal to transient response plus steady state response. So what is the transient response? We got A into e power minus t by RC plus, this is the steady state response, Vm by square root of 1 plus omega RC square into sine of omega t plus pi minus tan inverse omega RC. So this is Vc of t. Now to find the constant A, so at t equal to 0, what is the Vc of 0 is nothing but 0. There is no initial voltage. So if I substitute in this expression, 0 is equal to A into 1 because e power 0 is 1 plus Vm by square root of 1 plus omega RC square sine of pi minus tan inverse omega RC. Right? So what is A here? We will get minus Vm by square root of 1 plus omega RC square sine of pi minus tan inverse omega RC. Now if I substitute, what is the Vc of t? We will get here is now like this. So Vc of t is equal to A, that is minus Vm by square root of 1 plus omega RC square into sine of pi minus tan inverse omega RC into e power minus t by RC plus steady state response Vm by square root of 1 plus omega RC square sine of omega t plus pi minus tan inverse omega L omega RC. Right? So this is the total response. Now again, transient free condition. So how to make transient free? Right? So this is the transient term. To make this 0, if I make this pi minus tan inverse omega RC 0, so sine 0 is 0, so the total this term will be vanish. So pi minus tan inverse omega RC will be 0. Then only we will get Vc of t is equal to only steady state response. So what is the transient free condition here? Pi is equal to tan inverse omega RC. So that is for let. Now if V of t is equal to Vm cos omega t plus pi, suppose. Now what is the transient free condition? We will get pi is equal to only plus pi by 2 will be added. So tan inverse omega RC plus pi by 2, same as it is. Now at t is equal to t naught, so I will write same. So we get the transient free condition is omega t naught plus pi is equal to tan inverse omega RC for sinusoidal signal. Omega t naught plus pi is equal to tan inverse omega RC plus pi by 2 for cos sinusoidal input signal and cos input signal. So these are the two transient free conditions at t equal to t naught if the switch is closing. So same as it is in the RL circuit. Right? Now we will solve one or two problems on this concept. Now we will solve one problem on this RL network. So question is given like this: V of t is given Vm sin omega t and f is equal to 50 Hz, and the R 5 ohms, L is 0.01 Henry. Now at what value of t naught transient free condition is obtained? Right? Now we have to remember the transient free condition at t equal to t naught. So what is the transient free condition? Omega t naught plus pi is equal to tan inverse omega L by R. Right? Now here sin omega t plus pi, so pi is nothing is given, so it is 0, so pi is equal to 0, so omega t naught is equal to tan inverse omega L by R. Now to find t naught, so what we need to find? Omega. So f is given, so what is omega? 2 pi f, so 2 pi into that is 50, so that is 100 pi. Right? Now if I substitute 100 pi and omega and this L and R, so omega is 100 pi into t naught is equal to tan inverse omega means 100 pi into L is given 0.01 by this is 5. Now if I solve, I will get t naught here. So 0.0, so this is tan inverse, I will get directly pi by 5, and here 100 pi into t naught. So what is t naught? So t naught is nothing but tan inverse pi by 5 by 100 pi. Now to solve this tan inverse pi by 5, so we need to use calci tan inverse pi by 5. So don't use degree mode. So you have to use in the radians mode. So shift tan inverse pi divided by 5 divided by this is 100 pi. 100 pi. So 1.78 millisecond. 1.78 millisecond is the T0 value to obtain the transient free condition. Next we solve one more problem in the RC network. So this is given cos t, the signal, and find T0 to obtain transient free condition. Now for RC network we know this is a cos t. So omega T0 plus pi is equal to tan inverse omega RC plus pi by 2 is the condition for transient free because cos signal is given. What is pi? Pi is equal to 0 because cos of t plus pi. So pi is equal to 0. And what is omega? Omega is 1 radian per second. Right? Now if I substitute in this, so 1 into T0 plus 0 is equal to tan inverse omega RC. Omega is 1 into R is 1. Everything is 1. So plus pi by 2. Now tan inverse 1 is nothing but 45 degrees. So I will write as pi by 4 plus pi by 2. So this is T0. So what is this one? This is 4. This is 3 pi by 4. This is T0 in seconds. So it's very simple to find 3 pi by 4. 2.356 seconds. That is T0. That means when T0 is equal to 2.356, then we will get the transient free condition. Right? 3 pi by 4. Right? Okay. So this is about the AC transient. Right? So next we will start the two-port networks. Right? Next lecture we'll see two-port networks. So this is a very easy topic and we'll get questions from these two networks. Right?